Join me, everybody. Today we're going to be reading the first chapter of David Griffith's Introduction to Quantum Mechanics. If you want to see a quick summary of the table of contents of this book, check out the video right here. If you want to see a quick 7-minute summary or run through of this chapter here, check out the video over here. In today's video, we're going to be peeping this chapter, reading it in details. Maybe we're going to get through all of it. Maybe we're not going to get through all of it. We'll see. Let's start off. The Schrodinger Equation, section 1.1. Imagine a particle of mass m constrained to move along the x-axis, subject to some specified force F as a function of x, t, x being position, t being time. Figure 1.1. Figure 1.1, right here we got the object mass m and the force, and it is constrained to move along the x-axis, one-dimensional motion. The program of classical mechanics is to determine the position of the particle at any given time, x as a function of t. Once we know that, we can figure out the velocity. V equals derivative of x with respect to t, dx by dt. The momentum, P is equal to m times velocity. The kinetic energy, P is equal to 1/2 mass times velocity squared, or any other dynamical variable of interest. And how do we go about determining x as a function of t? We apply Newton's second law, F equals ma. For conservative systems, the only kind we shall consider, and fortunately the only kind that occur at the microscopic level, the force can be expressed as the derivative of the potential energy function. F is equal to negative partial derivative of V, the potential energy, with respect to x. So partial V, partial x. And Newton's law reads m second derivative of x with respect to time is equal to negative, this is the gradient, I'm assuming. Is that what they said here? Derivative of the potential energy. So I guess this is just the negative derivative of the potential energy. And this is the force. So here we have F, here we have m, and the second derivative of position with respect to time is a. So F equals ma, Newton's second law. This, together with appropriate initial conditions, typically the position and the velocity at time equals 0, determines x as a function of t. So this is a summary of classical mechanics. Quantum mechanics approaches this problem quite differently. In this case, what we're looking for is the particle's wave function, which is this Greek letter psi as a function of x and t, position and time. And we get it by solving the Schrodinger equation. Here is the Schrodinger equation. They put a little colon. This is what it looks like. Very important equation. We're going to be slamming this equation for the entire book, basically. You're going to learn to solve it for different potentials V and find the wave function over here. Here, I, which you can see right over here, is the square root of -1, and h bar, which you can see right here, is Planck's constant, or rather, his original constant, h, without the bar, divided by 2 pi. So here they show you Planck's constant. I think this is called the reduced Planck constant. This is the original Planck constant, h. If you divide h by 2 pi, you get the reduced Planck constant, and that is equal to this number here, 1.054573 times 10 to the negative 34. The units are joule seconds, so joule times seconds. Joule is a unit of energy, second is a unit of time. The Schrodinger equation plays a role logically analogous to Newton's second law. Given suitable initial conditions, typically psi at position x at time 0, so the initial temporal conditions of psi, the Schrodinger equation determines psi as a function of x, t for all future time. Just as in classical mechanics, Newton's law determines x as a function of t for all future time. Amazing! This first section basically tells you, hey, do you know F equals ma from classical mechanics? Everything we get from this and all the things we get from classical mechanics is pretty much the same stuff we're doing in quantum mechanics, except we have a new equation, which they say is analogous. They use the word analogous here. This Schrodinger equation is analogous to Newton's second law, but what we're looking for is not the position, x of t, of the particle. We're looking for the wave function, psi, as a function of x of t, of the particle, or whatever we're talking about. A little bit strange, but okay, let's accept that as true and move on. We're going to go to the second section, the statistical interpretation. But what exactly is the wave function, and what does it do for you once you've got it? After all, a particle, by its nature, is localized at a point, whereas the wave function, as its name suggests, is spread out in space. It's a function of x for any given t. How can such an object represent the state of a particle? Particle is in italicized. The answer is provided by Born's statistical interpretation. Born is a gentleman that worked on quantum mechanics sometime in the 1910s, 1920s. And he developed this thing called the statistical interpretation, which is what we're reading about in this second section. So the statistical interpretation says the absolute value, which is what these brackets are, of psi, the wave function, squared. So you take the wave function, you take its absolute value, you square that. This gives you the probability of finding a particle at point x at time t, or more precisely, and then they give you this box over here, the integral from a to b of the absolute value of the wave function squared with respect to dx, or with respect to x, the variable of integration. This equals the probability of finding the particle between a and b at time t. Interesting. So it's a probabilistic type of thing going on over here. Probability is the area under the graph of psi squared, the wave function squared, absolute value. I'm just going to say psi squared because absolute value, you know what this is by the brackets here, the little straight up and down pipe brackets. For the wave function in figure 1.2, figure 1.2 is right here. Let's actually read this. A typical wave function, the shaded area represents the probability of finding the particle between A and B. This is the shaded area. A and B are its bounds. The particle would be relatively likely to be found near A and unlikely to be found near B. What? Let me actually... unlikely to be found at capital B. So because the wave function boom boom moves around and goes to 0, you can see the wave function here with respect to x. Right here at position B, it's very close to 0. So you would assume that the probability of finding the particle at exactly this part B, the location x that is denoted by B, is very low. But this location A, capital A, is where the probability distribution is very, very high. So at location A, you might assume, or more probably, you're going to find the particle there. More times than not, you're going to find the particle there. And part C is kind of in the middle. You might find the particle here, sometimes you might not. Part B, you will rarely find it. Let's keep reading here. The statistical interpretation introduces a kind of indeterminacy into quantum mechanics. For even if you know everything the theory has to tell you about the particle, to wit, its wave function, still you cannot predict with certainty the outcome of a simple experiment to measure its position. All quantum mechanics has to offer is statistical information about the possible results. The indeterminacy has been profoundly disturbing to physicists and philosophers alike, and it is natural to wonder whether it is a fact of nature or a defect in the theory. This is crazy, bro. This gives me chills just reading it. This theory, which is one of the most widely trusted, I don't know if trusted is the right word, let's say like the most theory that has given the best results, I guess, in nature, tells you that there's some kind of indeterminacy going on. And also it tells you this fact has been disturbing to physicists and philosophers. And they tend to question whether this is a fact of nature, this is how nature actually works, or there's something wrong with quantum mechanics. Very interesting way to start the chapter. Suppose I do measure the position of the particle, and I find it to be at point C, which is right here. Actually, they also give you this little point 4, which you can read down here, but I'm not going to do that. You guys can read it if you want. The book is free online. You can just search up the chapter or the title of the book. You should find it. Question: where was the particle just before I made the measurement? There are 3 plausible answers to this question, and they serve to characterize the main schools of thought regarding quantum indeterminacy. So here are the answers. You have answer 1, answer 2, and answer 3. They come in the form of like beliefs or positions, things that you believe in. So the first is the realist position, the orthodox position, and the agnostic position. Let's go one at a time. The particle was at C. This certainly seems reasonable. And It is the response the response Einstein advocated. Note, however, that if this is true, then quantum mechanics is an incomplete theory, since the particle really was at C, and yet quantum mechanics was unable to tell us so. To the realist, indeterminacy is not a fact of nature, but a reflection of our ignorance. As Despanat put it, Despanat, the position of the particle was never indeterminate, but was merely unknown to the experimenter. Evidently, psi is not the whole story. Some additional information, known as the hidden variable, is needed to provide a complete description of the particle. Very interesting. This hidden variable thing comes up in this thing called Bell's experiment, I believe. And it was like kind of a fight between Einstein and some stuff, because Einstein was a realist. He thought there was something wrong with quantum mechanics and that it was an incomplete theory. But I think later on people showed that it was. I'm not sure. We're going to keep reading. I'm just spewing out some stuff that I've heard before. The orthodox position. The particle wasn't really anywhere. It was the act of measurement that forced it to take a stand. Though how and why it decided on the point C, we dare not ask. Jordan said it most starkly. I don't know who Jordan is. Maybe that's a last name, actually, even though it's more commonly a first name. Observations not only disturb what is to be measured, they produce it. We compel the particle to assume a definite position. This view, the so-called Copenhagen interpretation. Google search this, check Wikipedia if you're interested. This is one belief of quantum mechanics. I think it's the most widely accepted one currently. I'm not sure. Is associated with Bohr, another name, last name, I don't know. Niels Bohr, I think is his full name. Bohr and his followers believe this, I guess. Or it's associated with them. So Bohr and his boys figured out the Copenhagen interpretation. Among physicists, it has always been the most widely accepted position. Okay, gang. Note, however, that if it is correct, there is something very peculiar about the act of measurement, something that almost a century of debate has done precious little to illuminate. David Griffiths always has such a weird way of writing. Precious little to illuminate. Like, what a poet. Let's read the last point. The agnostic position. Refuse to answer. This is not quite as silly as it sounds. After all, what sense can there be in making assertions about the status of a particle before a measurement, when the only way of knowing whether you were right is precisely to make a measurement, in which case, what you get is no longer before the measurement. Okay, it is metaphysics in the pejorative sense of the word. Pejorative, I think, means bad. I'm not sure. To worry about something that cannot, by its nature, be tested. Pauli said, Pauli, I think, is Wolfgang Pauli, W first name, Wolfgang. One should no more rack one's brain about the problem of whether something one cannot know anything about exists all the same, than about the ancient question of how many angels were able to sit on the point of a needle. Number 7. They actually like reference what he was talking about. Great. For decades, this was the fallback position of most physicists. They try to sell you the orthodox answer, which is this one here, the most widely accepted one. They try to sell you... Wait, where were we? Oh yeah. For decades, this was the fallback position of most physicists. They tried to sell you on the orthodox answer. But if you were persistent, they'd retreat to the agnostic response and terminate the conversation. That's jokes. Okay, so we have 3 different ways of thinking of quantum mechanics. The first one is quantum mechanics is not real. We're bugging. We need to find a new theory. This was Einstein, one of the smartest dudes that lived 100 years ago. He was like, quantum mechanics is incomplete. We need to find something else. There must be some hidden variables. Why he's talking about hidden variables is because quantum mechanics believes that this psi, this symbol psi, the wave function, holds all information about the system that you're measuring. Just like in classical mechanics, if you know the position as a function of time for the particle, you know what it's doing for all of time, then you can say everything you have to say about the system. You could say its energy, its momentum, you could talk about anything you want. The same thing in quantum mechanics. This psi, people believe, holds all of the information about the system. So Einstein is saying, okay, if psi doesn't know how to tell you where the particle is before measurement, then it's not the whole story, right? Right here. So there must be a hidden variable, something missing from psi further information about the system that knows where the particle is before measurement. And we need to find this thing to have a complete theory, a new quantum mechanics, an improved quantum mechanics. But I think this is not the way people believe it. They believe in this Copenhagen interpretation. The particle wasn't really anywhere. What does this mean? This is crazy. Basically, before you measure, the particle is in all locations at the same time. The particle lives kind of like a little wave or something, and then when you measure it, it collapses into a specific point, which is what they show you right here. After measurement, the wave function becomes this, meaning 100% of the time you measure it, then the particle will be found at this location. But before measurement, the particle could be doing something crazy like this. We have no idea. So this is the orthodox position. And the agnostic position is saying, we don't know, cuz. All right, let's keep reading. Until fairly recently, all three positions, realist, orthodox, and agnostic, had their partisans. But in 1964, John Bell, who was I swear I saw the name. Oh yeah, the guy that did the hidden variable experiment. But in 1964, John Bell astonished the physics community by showing that it makes an observable difference whether the particle had a precise, though unknown, position prior to measurement or not. Bell's discovery effectively eliminated agnosticism as a viable option and made it an experimental question whether 1 or 2 is the correct choice. I'll return to this story at the end of the book, but you will be in a better in the book when you will be in a better position to appreciate Bell's argument. For now, suffice it to say that the experiments have decisively confirmed the orthodox interpretation. Experiments have decisively confirmed the orthodox interpretation. A particle simply does not have the precise position prior to measurement any more than the ripples on a pond do. It is the measurement process that insists on one particular number and thereby, in a sense, creates the specific result, limited only by the statistical weighing imposed by the wave function. Okay, this kind of confused me a little. Maybe I'm reading too much. Maybe I need to take a break. We're going to keep going. But if you're interested in what Bell did, search up Bell's inequality or Bell's experiment. And he basically looks for hidden variables and says these guys can't exist or something like that. I don't know. You got to read it. It's complicated. What if I made a second measurement immediately after the first? Would I again get C? Or does the act of measurement cough up some completely new number each time? On this question, everyone is in agreement. A repeated measurement on the same particle must return the same value. Indeed, it would be tough to prove that the particle was really found at C in the first instance, if this could not be confirmed by immediate repetition of the measurement. How does the orthodox interpretation account for the fact that the second measurement is bound to yield the value C? It must be that the first measurement radically alters the wave function so that it is now sharply peaked about C, figure 1.3, right here. So before measurement, the particle's wave function looks like this. You can measure it. It has a probability of being in many locations, very small chance of it being at B, medium chance being at C, very high chance at being at A. But it could be anywhere, right? It's a probability. So if you measure the system 100 times, in this scenario, maybe 1 out of 100 times is going to be at B, maybe 9 or 10 is going to be at C, and maybe like the rest are going to be at A. But it could be anywhere. So you make a measurement, and that measurement radically changes the wave function so it looks like this. So it appears at C, then the wave function changes from that distribution we saw earlier, and it looks like this. Where if you again measure it, there's no chance you're going to find the particle here because the probability distribution is straight up 0 in this location. It's in fact 0 everywhere except right here at point C. So you measure it, you're going to have almost 100% chance of finding it right here. Does that make sense? This is after the first measurement. And what do you mean by measurement? We're talking so ethereally right now. Don't stress, guys. We're just reading the book. No spoilers, all right? You can't ask what's going to happen at the end of the book. You got to just keep reading. We say that the wave function collapses, and this is bolded, upon measurement to a spike at point C. It soon spreads out again in accordance with the Schrodinger equation, so the second measurement must be made quickly. Interesting. There are then two entirely distinct kinds of physical processes. Ordinary ones, in which the wave function evolves in a leisurely fashion under the Schrodinger equation, and measurements in which psi suddenly and discontinuously collapses. Think about this. Quantum mechanics now splits things up into two different processes. The one where things are just chilling, time moves on, nothing is happening, or maybe not nothing is happening, but I don't know, nature proceeds as it is. Like, for example, a bird is flying. This is an ordinary process. But then when you take out your binoculars and look at the bird, this is now not an ordinary process. This is classified as a measurement. In classical mechanics, you don't do this. There's no measurement, ordinary, there's nothing like this. You just know what the system is doing. The system kind of sounds a little scary, a little weird. Just imagine anything. A ball, drop a ball and it bounces, throw a ball in the air and it does that parabola thing that you calculated. A car or a block sliding down a ramp. Any kind of classical mechanics problem, there's no talk about this measurement and ordinary processes, but in quantum mechanics there is. All right, we got an example. Should we read the example or should we just skip it? Okay, I guess we should read it because we finished section 1.2, which is pretty insane. And then section 1.3 is probability, which personally I'm not a big fan of. I honestly might take a break before going through this, or I might push through it. We will see, but let's do this example. Example 1.1, electron interference. I have asserted that particles, electrons for example, have a wave nature encoded in psi. How might we check this in the laboratory? The classical nature of a wave phenomenon is interference. Two waves in phase interfere constructively, and out of phase they interfere destructively. The wave nature of light was confirmed in 1801 by Young's famous double-slit experiment, showing interference fringes on a distant screen when a monochromatic beam passes through two slits. If essentially the same experiment is done with electrons, the same pattern develops, confirming the wave nature of electrons. That's crazy. Now suppose we decrease the intensity of the electron beam until only one electron is present in the apparatus at any particular time. According to the statistical interpretation, each electron will produce a spot on the screen. Quantum mechanics cannot predict the precise location of that spot. All it can tell us is the probability of a given electron landing at a particular place. But if we are patient and we wait for 100,000 electrons, one at a time, to make the trip, the accumulated spots reveal the classic two-slit interference pattern, figure 1.4. This is figure 1.4. Buildup of the electron interference pattern. A, 8 electrons. B, 270 electrons. C, 2,000 electrons. D, 160,000 electrons. And you can see clearly there is constructive interference at these bright fringes right here, and destructive interference at these dark fringes right here. So normally you think of electrons as just tiny balls orbiting around. You know, this is the nucleus of the atom. You got electrons zooming around. But you shoot them through a double slit experiment and they show behavior indicative of waves. So these single electrons behave like waves, which is very interesting. Reprinted courtesy of the Central Research Laboratory, Hitachi, Japan. Amazing. Of course, if you close off one slit or somehow contrive to detect which slit each electron passes through, the interference pattern disappears. The wave function of the emerging particle is now entirely different. In the first case, because the boundary conditions of the Schrodinger equation have been changed, and in the second, because the collapse of the wave function upon measurement. But with both slits open and no interruption of the electron in flight, each electron interferes with itself. It didn't pass through one slit or the other, but through both at once, just as a water wave. Imagining a water wave impinging on a jetty with two openings. Jetty? What is this? Interferes with itself. There's nothing mysterious about this. Once you have accepted the notion that particles obey a wave equation, the truly astonishing thing is the blip by blip assembly of the pattern. In any classical wave theory, the pattern would develop smoothly and continuously, simply getting more intense as time goes on. The quantum process is more like a pointillist painting of Seurat, the pointillist guy. The picture emerges from the cumulative distributions of all individual dots. This reminds me of that meme where if you look at it, it's just the classic like projectile two-slit experiment, and if you don't look at it, it is the wave interference pattern two-slit experiment. So, okay, whatever you think of this chapter, I don't know, whatever way you're trying to put it into your head, don't worry. I think the best way to go through quantum mechanics is just bulldoze through and keep reading, keep trying to understand. You might be asking what kind of questions are we going to be asked here. We haven't really seen any problems with the Schrodinger equation. Don't stress about that yet. We're just going to keep reading, see where the book takes us, and we'll see when the time comes. Alright, I'm going to take a little break before probability. I'll see you guys in a second. Alright, moving on with probability. Discrete variables. Because the statistical interpretation, probability plays a central role in quantum mechanics. So I digress now for a brief discussion on probability theory. It is mainly a question of introducing some notation and terminology, and I shall do it in a context of a simple example. Imagine a room containing 14 people whose ages are as follows. 1 is 14, 1 15, 3 people are 16, 2 are 22, 2 are 24, 5 people are age 25. If we let n, parentheses, lowercase j, represent the number of people of age j, then we have n 14, so the 14th person of 14 age equals 1. N of 15 is 1, n of 16 is 3. Basically what we see here written in a different way. N of 25, so the number of people that are 25 is 5. Histogram showing the number of people n of j with age j, for example, in section 1.13. So here's nj, here are all the ages. We see one block here for 14 showing us that there's one person of age 14, one of 15, and 5 people of age 25. While n of 17, for instance, is 0, the total number of people in the room is... while n for 17, for instance, is 0, boom, the total number of people in the room is, capital N is equal to summation sign of starting at j equals 0 going up to infinity of n as a function of j. So we start at j equals 0, check what n is, then j equals 2, check what n is, add those two numbers together, so on and so forth. So basically what this function is telling you is take all these squares here from j equals 0 all the way to infinity and add them up together. In this case, we can just count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. In our example, of course, n is 14 because they told us here. Imagine 14 people in a room. Amazing. Figure 1.5 is a histogram of the data. The following are some questions one might ask about this distribution. Question 1. If you selected one individual at random from this group, what is the probability that this person's age would be 15? 15, so one person out of the 14 in the room. One chance in 14, since there are 14 possible choices, all equally likely, of whom only one has that particular age. If p as a function of j is the probability of getting age j, then p of 14 is equal to 1 over 14. P of 15 is equal to 1 over 15, because we have one person age 15. P of 16 is 3 over 14, because 16 has 3 people, and so on. In general, P of j is defined as n of j divided by n being the total number of people, which we saw was 14, and nj being that specific number of people with that specific age. Notice the probability of getting either 14 or 15 is the sum of the individual probabilities, in this case 1/7. So 1 over 14 is the probability of getting age 15 at random, and 1 over 14 is also the probability of getting age 14. 1 over 14 plus 1 over 14 gives you 1 over 7. In particular, the sum of all probabilities is 1. The person you select must have some age. So the summation from j equals 0 to j equals infinity of the probability function here, if p of g is the probability of getting a specific age, the summation of all the probabilities should give you 1. Question 2. What is the most probable age? 25, obviously. 5 people share this age, whereas at most 3 have any other age. The most probable j is the j for which p of j is a maximum. Question 3. What is the median age? 23. For 7 people are younger than 23 and 7 people are older. The median is that value of j such that the probability of getting a larger result is the same as the probability of getting a smaller result. Question 4. What is the average or mean age? Answer. You add all of the people of a specific age. So we have one person of 14, one person of 15, 3 people at 16, 2 people at 22, 2 people age 24, and 5 people age 25. All of these we get at the numerator and we divide by the total number of people, and we get 21 being the average age in that room. In general, the value of j, which we shall write thus, boom. So we got these interesting brackets. I think these are straight up called brackets. Maybe I'm skipping a little ahead. The average value of j. So basically, if you see something around this, a symbol here, these brackets here, it's basically saying the average of whatever is inside those brackets. So maybe here, all right, we're just gonna keep reading. Average of j is equal to sum of j times n of j, all of that divided by n, which equals the sum from j equals 0 to j equals infinity of j times p of j. This is getting a little weird for me. This is why I don't really like probability too much, but we're just going to keep bulldozing through. Notice that there need not be anyone with the average age or the median age. In this example, nobody happens to be 21 or 23. In quantum mechanics, the average is usually the quantity of interest. In that context, it has come to be called the expectation value. It's a misleading term since it suggests that this is the outcome you would be most likely to get if you made a single measurement. That would be the most probable value, not the average value. But I'm afraid we're stuck with it. So expectation value. We're just going to keep reading because it's getting a little confusing here, personally speaking. Question 5. What is the average of the squares of the ages? You could get 14 squared equals 196 with probability 1 over 14. 15 squared equals 225 with probability 1 over 14. 16 squared equals 256 with probability 3 over 14, and so on. Probabilities here seem to be the same as the ones where we just looked for the specific ages in question 1 over here. The average then is, so here we have j squared, which is the squares of the ages, and the brackets around it are denoting the average, right? Because we learned that up here. So this is the summation from j equals 0 to j equals infinity of j squared times the p as a function of j. So it looks very similar to what we had over here, except we just take this thing here and put it inside the sum. So here we have j squared, here we have j squared, here we have j, here we have j. Looks good? In general, the average value of some function of j is given by, here we have a function of j, f as a function of j. We have the brackets that denote average of this thing, and we get the same thing, summation from j equals 0 to infinity. That function, the thing over here, you plop it in there and you multiply it by p of j. You can see the same pattern. Here we have 3 examples. Here's one, f of j. F of j is being multiplied inside this sum. This sum looks identical to this one, except we have j squared. Here we have j squared. And this sum looks identical to the other 3, except here we have j and here we have j. So this is going to come up quite a lot. That's why they're showing you this, and they're actually boxing it because it is very important. If you have no idea what you're looking at here, don't stress about it. Just note it in your mind. You can always go back to this chapter if needed. Equations 1.6, 1.7, and 1.8. So I guess here, 1.6, 1.7, 1.8 are, if you like, special cases of this formula. So this formula creates instances of itself with specific, differences in each scenario. It is actually pretty cool that this one is also an instance of that formula. The sum of all probabilities equaling 0. This we're going to check out in the next chapter, which is called normalization. All right, let's keep going. Beware, the average of the squares is not equal in general to the square of the average. So this is the average of the squares. J is the thing that we're trying to average. We square it and then we take the average. Here is the square of the average. So J is the thing we're taking the average. You can see the brackets, and you square that entire thing. What this sentence is saying, these two are not in general equal. For instance, if the room contains just 2 babies, age 1 and 3, then the average of the squares of the ages is 5, but the square of the average of the ages is 4. If this is sounding a little confusing, keep going, don't stress too much. Now there's a conspicuous difference between the two histograms in figure 1.6, this one here. Even though they have the same median, the same average, the same most probable value, and the same number of elements, the first is sharply peaked about the average value, whereas the second is broad and flat. So they're talking about this thing right here. You can see right here, the distribution is very sharp. Well, here it is more flattened, but they do have a lot of similar qualities about themselves. The first might represent an age profile for students in a big city classroom. The second, perhaps, a rural one-room schoolhouse. We need a numerical measure of the amount of spread in a distribution with respect to the average. The most obvious way to do this would be to find out how far each individual is from the average. So we have another important equation here. We have delta J equals J, the specific age that you're looking at, minus the average of J. So this is basically telling you how far is J from the average of J. In this scenario, this singular instance, the person at the age of 6 is very close to the average. He's 1 age away. But in this scenario, this person here is quite far from the average. He's 9 and the average is here at 5. So this defines the spread over here. This will help you figure out how spread out the distribution is, which is important. To compute the average of delta J, trouble is, of course, that you get 0. So here we have delta J with the average brackets. We can compute this using this formula here, right? So we have the average brackets and we're just going to put delta J in there. Remember, delta J just gets brought here. You multiply it by the P of J here. And what we get is delta J in here. You just replace delta J with its definition from here. Boom, and you multiply by P of J. Then it looks like you simplify it. It looks like you distribute this P of J to the first J and to this average of J. And then it also looks like you split up the sum. So this first sum becomes J times P of J. The second one, since average of J is a constant, it doesn't depend on the summation. You pull it out of the summation and you just get this. Then what we have is average of J from this, which you can get just by going to the original definition here. And over here, this summation is equal to 1, which you can get by going all the way up here and looking at this. Amazing. So now we have average of J minus average of J, which gives you 0. Note that J is constant. It does not change as you go from one member of the sample to another. So it can be taken outside the summation, which is the step they do here. To avoid this irritating problem, you might decide to average the absolute value of delta J. But absolute values are nasty to work with. Instead, we get around the sign problem by squaring before averaging. I see. So the problem here is you're trying to find the average of delta J and you get 0, which is not good, I guess. I don't know. If I got this, I'd just be like, sick, the average of this is 0. But I guess it's not 0. So they're going to try to find what this equals in a different manner. Here, what they do, I guess, is square it and then take the average. So delta J squared, take the average. And in order to not write this so many times, they redefine this as this symbol, sigma squared. This quantity is known as the variance of the distribution. Sigma itself, the square root of the average age of the square of the deviation from the average. My boy Griffith know when we're struggling. So this thing, sigma itself, is called the standard deviation. Cool. The latter is the customary measure of the spread about J. Interesting. The latter. So what we're looking for is just the variance here, which I guess they calculated from this. There is a useful little theorem on variances. Honestly, guys, if you're interested, you could look at this. I'm not going to go through all this math here. It looks like they calculate this, boom, 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 then they get this. So basically, this sigma squared, which is known as the variance, right here, is calculated after some math, which is similar to this. If you're interested, look through it. And you get this over here. So what the variance is the average of the square of the ages minus the square of the average of the ages. Taking the square root of this, the standard deviation itself can be written as the square root of this difference here, which I'm not going to say because we're going to gulp every time. In practice, this is a much faster way to get sigma than by direct application of 1.11. 1.11 here. This. Oh, I guess so they find like an easier way of calculating than doing this computation using the rule that we found over here. Okay, man, probability always like boils my brain. Let's keep going. We were here. Simply calculate this, the average of the squares of the ages and the square of the average of the ages. I'm saying ages because that's our problem, but J here could be any arbitrary parameter related to the problem that you're working with. Subtract and take the square root. Incidentally, I warned you a moment ago that the average of the square of the ages is not in general equal to the square of the average of the ages, since sigma squared is plainly non-negative from its definition, 1.11. Okay, it's non-negative. Okay. I guess it's non-negative because it's squared here. Okay. Equation 1.12 over here implies that this average of the squares of the ages is bigger than or equal to the square of the average of the ages. And the two are equal only when sigma is equal to 0, sigma being the standard deviation, which is to say for distributions with no spread at all, every member having the same value. Guys, if you feel confused, I am right there with you. We're just reading this, getting the information in our head. We're going to use this in a concrete problem, hopefully later in the chapter, and it's going to make more sense. Of course, just seeing it right here and reading it, it's scary. And Mr. Griffiths understands this, but it's the first time we're reading this, so it's okay if it's a little scary. Continuous variables. Let's read this, and we're going to take another break because probability always eats my brain. So far, I have assumed that we are dealing with discrete variable, a discrete variable. That is, one can take on only certain isolated values. In the example, J had to be an integer since I gave only ages in years. But it is simple enough to generalize to continuous distributions. If I selected a random person off the street, the probability that her age is precisely 16 years, 4 hours, 27 minutes, and 3.333 seconds is 0. The only sensible thing to speak about is the probability that her age lies in some interval, say between 16 and 17. Pretty cool. I mean, it makes sense. If the interval is sufficiently short, this probability is proportional to the length of the interval. Okay. For example, the chance that her age is between 16 and 16 plus 2 days is presumably twice the probability that it is between 16 and 16 plus 1 day, unless I suppose there was some extraordinary baby boom 16 years ago on exactly that day, in which case we have simply chosen an interval too long for the rule to apply. If the baby boom lasted 6 hours, we'll take intervals of a second or less to be on the safe side. Typically, we're talking about infinitesimal intervals. Thus, probability that an individual chosen at random lies between x and x plus dx is equal to this little, it's not a p anymore, this is a Greek letter rho. Rho is a function of x times dx. The proportionality factor, rho is a function of x, is loosely called the probability of getting x. But this is sloppy language. A better term is probability density. and this is bolded. The probability that x lies between a and b, a finite interval, is given by the integral of rho of x. Probability subscript ab, so the probability of finding, the probability of getting a specific event, whatever this probability density defines, between a and b is the probability density integrated over dx, the variable of choice in this specific range a and b. And the rules we deduced for discrete distributions translate in the obvious way. The integral from negative infinity to infinity of the probability distribution over with respect to dx is equal to 1. So this equation here is exactly the same as the one with the summation sign that we saw here. We just changed the summation sign to an integral, and also in this specific age it starts at 0 because age starts at 0. You're not a negative age ever, and it goes to infinity because you push it on forever in case somebody lives very, very old. But in an arbitrary scenario where the variable you're looking at is not age, it's something that can take a negative value, then the sum can go to negative infinity, and the integral, which is right here, can also go to negative infinity. So we have the same thing. These little brackets, which mean the average of x, is the integral from negative infinity to infinity, x times the probability distribution here with respect to dx. And in general, we have this, which is very similar to the boxed equation we saw here. We just changed the summation to an integral. The average of some arbitrary function of x is the integral over all space of that function times the probability density with respect to dx. The variance is defined as the average of the square of delta x, or another way of writing it, a simpler way for computational purposes, is taking this difference here. Specifically, the average of the square of x, whatever x is, your variable of choice, minus the square of the average of x, whatever x is. Before it was ages, and like now we're moving on, probability can be applied to anything, not just 8 ages in a room. So x could be any variable. Awesome. Let's finish with this example, and then we got some problems and normalization in the next section. Amazing. Probability isn't so bad. I don't like it the most though, but it's important for quantum. Suppose someone drops a rock off a cliff of height h. As it falls, I snap 1,000,000 photographs at random intervals. On each picture, I measure the distance the rock has fallen. Question: what is the average of all those distances? That is to say, what is the time average of the distance traveled? Interesting problem. We're not going to solve it. We're just going to read the solution. The rock starts at rest and picks up speed as it falls. It spends more time near the top, so the average distance will be surely less than h over 2. Ignoring air resistance, the distance x at time t is, x as a function of t is, this is in the equation to find how much an object has moved if you drop it in gravity. So 1/2 times g, the gravitational constant, times time squared, the amount of time the object has fallen. The velocity, derivative of x with respect to time, equals gt. The total flight time is capital T square root 2h over g. How do you find this capital T? Probably got to do some integral or something. I don't know. We're not doing classical mechanics now. If you're interested in this, take a look at falling objects. The probability that a particular photograph was taken between t and t plus dt is dt over capital T. Why is this the case? Because this is the total amount of time, and this is that specific difference in time that we are looking for the probability in. So the same thing as what we did before. It's like dt is the age of the specific person in the room that you're trying to find the probability of choosing at random, and capital T is the total number of people in that room that have ages. So the probability that it shows a distance in the corresponding range x to x plus dx is dt over t. We have values for all of this, so t, capital T, can be replaced by this, and dt can be replaced by dx and gt. So we have gt here, dx, and this square root from the capital T. And then we get this thing, which is looks like a function, and the little dx, something with respect to x. Thus the probability density, equation 1.14. Let's check equation 1.14. Here, probability density is, I'm assuming just this stuff here before the dx. Is that correct? Before the dx. That is rho of x. Is that true? Yeah, looks like that's the case. So 1 over 2 square root hx, 1 over 2 square root hx, this is the probability density of finding the object. So I guess they're solving the problem here with some stats or some probability. X has to be between 0 and capital H. Outside this range, of course, the probability density is 0. We can check this result using equation 1.16. 1.16, the summation of all of the probabilities over all of the variable that you're looking at is 1. So from 0 to h, because our variable is x, we integrate this, we do the integral, and we get 1, which is good. The average distance is average x. Integrate from 0 to h. You multiply this little x here, remember, because we have this equation here. If you want to find the average of x, you multiply x inside by the probability distribution. So first we found the probability distribution. Here it is. Now we're finding the average of x, which is what the question is asking us. Here is the probability distribution. Here is x. This is just a integral, and it looks like a pretty simple one. It's a polynomial. Right? X to the power of 1 here, x to the power of minus 1/2. Combine those powers, do an integral, pull out the constants, and we get h over 3, which is somewhat less than h over 2 as anticipated. Figure 1.7 shows the graph rho of x. Notice that the probability density can be infinite, though probability itself, the integral of p, must of course be finite, indeed less than or equal to 1. Amazing. So we have some problems here, and we got normalization. All right, we're back with normalization. I took another break. Let's keep reading. Let's finish this video on time. We return now to the statistical interpretation of the wave function, equation 1.3, which was up there, the third equation, which says that absolute value squared of the wave function is the probability density for finding the particle at point t at time t. It follows, equation 1.16, that the integral of the absolute value squared of the wave function over all x must be 1. The particle's got to be somewhere. So the integral from negative infinity to infinity with respect to dx, so we're integrating over all space, of the absolute value squared of the wave function is equal to 1. You have to be able to find the particle somewhere. This is basically saying if you observe everywhere along the axis, in this case it's 1 dimensions, but you could do this integral in 3 dimensions. If you measure everywhere, you have a 100% chance of finding the particle somewhere. Without this, the statistical interpretation would be nonsense. However, this requirement should disturb you. After all, the wave function is supposed to be determined by the Schrodinger equation. We can't go imposing an extraneous condition on psi without checking that the two are consistent. Well, at a glance at equation 1.1 reveals that if psi of x comma t is a solution, so too is a times psi of x comma t, where a is any complex constant. What we must do then is pick this undetermined multiplicative factor so as to ensure that equation 1.20 is satisfied. This process is called normalizing the wave function. For some solutions to be the Schrodinger equation, the integral is infinite. In that case, no multiplicative factor is going to make it 1. The same goes for the trivial solution, psi is equal to 0. Such non-normalizable solutions cannot represent particles and must be rejected. Physically realizable states correspond to the square integrable solutions of the Schrodinger's equation. Don't stress about that, but wait a minute, exclamation point. Suppose I have normalized the wave function at time t equals 0. How do I know that it will stay normalized as time goes on and psi evolves? You can't keep renormalizing the wave function, for then a becomes a function of t and you no longer have a solution of the Schrodinger equation. Fortunately, the Schrodinger equation has a remarkable property that it automatically preserves the normalization of the wave function. Without this crucial feature, the Schrodinger equation would be incompatible with the statistical interpretation and the whole theory would crumble. Very interesting. This is important, so we'd better pause for a careful proof. To begin with, let's take the derivative with respect to time of the integral over all space of the square of the wave function. This equals, we can move the integral inside and it becomes a partial integral because this function is a function of two variables. I think you can interchange the integral and the derivative because of the fundamental theorem of calculus. Note that the integral is a function only of t, so I use a total derivative dt on the left. But the integrand is a function of x as well as t, so it's a partial derivative, partial t on the right. By the product rule, derivative with respect to t of the square of the wave function is equal to, we expand the way you take the square of a complex number, and psi here is a complex number, is the complex conjugate times the thing itself. So this is exactly the same as this, and we remove the absolute value. Then we can do the product rule, which is apply the derivative on one thing, apply the derivative on the other thing. Now the Schrodinger equation says that derivative of psi with respect to t is equal to all of this stuff, I h bar over 2m. Second derivative with respect to x of the wave function minus I over h, v, which is the potential times the wave function. So this is just the Schrodinger equation manipulated a little bit. And hence also taking the complex conjugate of equation 1.23, this one. Basically this equation, you take the complex conjugate. The complex conjugate, basically you find where I is, the imaginary number, and you change the sign in front of it. You add a negative sign. So in this case, it was negative. You add a negative sign, it becomes positive. In this case, it is positive. So you add a negative sign, it becomes negative. So partial derivative with respect to time of the absolute value squared of the wave function is equal to this stuff, right? They just combine this equation and this, and then they get this over here. I'm not going to go too deep into this. The video is going to be 17 hours long. The integral in equation 1.21. So here can now be evaluated explicitly. Boom. But psi of x comma t must go to 0 as x goes to plus to minus infinity. Otherwise, the wave function would not be normalizable. So the wave function has to go at the extremes to 0. It can't kind of like diverge, for example, x squared or x cubed does. Otherwise, the integral of the wave function squared is not going to be 1. It's going to be some infinite number. It follows that the derivative of this thing is equal to 0, and hence that the integral is constant independent of time. If psi is normalized at t equals 0, it stays normalized for all future time. QED. Awesome. Here we have a problem. Here we have another problem. Amazing. If that chapter was confusing, don't stress. We're going to see it in practice when we do a few problems. Let's keep reading with the second last section, I think, momentum. For a particle in state psi, the expectation value of x is expectation value, or average. And we have, actually, I'm a little uncomfortable saying average because there's most probable value, the average, the mean, the median, the expectation value. So just keep in mind, some of these things might have interesting definitions. We're going to have to see how they're actually used. But anyway, this thing here from the probability section, we have x multiplied by the probability distribution. In this case, it is the wave function squared, is equal to these brackets, expectation value. What exactly does this mean? It emphatically does not mean that if you measure the position of one particle over and over again, that this is the average of the results you'll get. See what I mean? Like, what the... In the probability section, this meant the average, but now it's not the average. So we're going to keep going. On the contrary, the first measurement, whose outcome is indeterminate, will collapse the wave function to a spike at that value that the value actually obtained. And the subsequent measurements, if they're performed quickly, will simply repeat the same result. Rather, this brackets x is the average of the measurements performed on particles all in the state psi, which means that either you must find a way of returning the particle to its original state after each measurement, or else you have to prepare a whole new ensemble of particles in each in the same state psi and measure the positions of all of them. Brackets psi, expectation value, I'll just call this expectation value x, is the average of these results. I like to picture a row of bottles on a shelf, each containing a particle in the state psi relative to the center of the bottle. A graduate student with a ruler is assigned to each bottle, and at a signal, they all measure the position of their respective particles. We then construct a histogram of the results, which should match absolute value squared of psi, and compute the average, which should agree with expectation value of x. Of course, since we're only using a finite sample, we can't expect perfect agreement. But the more bottles we use, the closer we ought to come. In short, the expectation value is the average of measurements on an ensemble of identically prepared systems. See, this is italicized, so this is what the expectation value means. It's a little bit more detailed than just the average. Not the average of repeated measurements on one and the same system. So maybe this is something that we should highlight. Quite interesting. Let's pick a cool color, something that we can see quickly. Some pink, not bad. Now, as time goes on, expectation value of x will change because of the time dependence of psi, and we might be interested in knowing how fast it moves. Referring to equation 1.25 and 1.28, we see that 16, to keep things from getting too cluttered, I'll suppress the limits of the integration. Okay, so the integration here is from negative infinity to infinity. The derivative of the expectation value of x with respect to time is this. Let's see what the answer is. This expression can be simplified using integration by parts. Awesome. If you're confused by integration by parts, this might be a good example to kind of play around with. I use the fact that partial x is equal to 1 and threw away the boundary term, ground that psi goes to 0 at plus infinity. Performing another integration by parts on the second term, we conclude, boom, what are we to make of this result? Note that we're talking about the velocity of the expectation value of x. Huh. Okay. Which is not the same thing as the velocity of the particle. Nothing we have seen so far would enable us to calculate the velocity of a particle. It's not even clear what velocity means in quantum mechanics. If the particle doesn't have a determinate position prior to measurement, neither does it have a well-defined velocity. All we can reasonably ask for is the probability of getting a particular value. We'll see in chapter 3 how to construct probability density for velocity given psi. For the moment, it will suffice to postulate that the expectation value of the velocity is equal to the time derivative of the expectation value of the position. So what we just found here is the expectation value of the velocity. Equation 1.31, right here, tells us then how to calculate expectation value of velocity directly from psi. Actually, it is customary to work with momentum, p is equal to m times v, rather than velocity. Expectation value of momentum is m times derivative with respect to time of the expectation value of x, which is equal to negative I h bar, integral over all space, in this case dx, complex conjugate of psi times the derivative with respect to x of psi. Let me write the expression for expectation value of x and expectation value of y in a more suggestive way. Expectation value of x is equal to the integral complex conjugate of psi, square brackets x, regular psi dx. Expectation value of momentum, integral complex conjugate of psi, square brackets this thing, which is negative I h bar, derivative with respect to position, times the regular psi. So you can see they look very similar, except the thing in the square brackets is different. We say that the operator x represents position and the operator negative I h bar, derivative with respect to position, or x, represents momentum. To calculate expectation values, we sandwich the appropriate operator between psi star, complex conjugate of psi, and psi, and we integrate. Very cool. That's cute. Bro, that's cute, but what about other quantities? The fact is, all classical dynamical variables can be expressed in terms of position and momentum. Kinetic energy, for example, is capital T 1/2 mv squared, p squared over 2m, p squared is momentum squared. The angular momentum is bolded. Angular momentum is a vector. L is equal to r cross product mv is equal to r cross product p. The latter, of course, does not occur for motion in one dimension. To calculate the expectation value of any such quantity q as a function of x and p, we simply replace every p by negative I h bar, derivative with respect to x, insert the resulting operator between psi star and psi, and we integrate. So here is how to find the expectation value of any operator. You basically sandwich the operator between psi star and psi, integrate over all space with respect to dx, and then you get the expectation value of the operator, which in general depends on position and momentum in classical mechanics. For example, the expectation value of kinetic energy is boom, and then we have this here. Equation 1.36 is a recipe for computing the expectation value of any dynamical quantity for a particle in state psi. It subsumes equation 1.34 and 1.35, 1.34 and 1.35, which is for position and momentum, as special cases. So this is the general case. For position and momentum, we have special cases. I have tried to make equation 1.36 seem plausible given Born's statistical interpretation, but in truth this represents such a radical new way of doing business as compared with classical mechanics that it's a good idea to get some practice using it before we come back in chapter 3 and put it on firmer theoretical foundation. In the meantime, if you prefer to think of it as an axiom, that's fine with me. So here's problem 1.6, 1.7, 1.8. I'm assuming those are some problems. Here we have a picture. And the final section, let's finish off here, guys. I know it's a long video. We're going to talk about it. We're going to do some problems in future videos. 1.6, the uncertainty principle. Imagine that you're holding one end of a very long rope and you generate a wave by shaking it up and down rhythmically, figure 1.8. Right here, boom, 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 boom. This guy's shaking it. If someone asked you precisely where is the wave, you'd probably think he was a little bit nutty. The wave isn't precisely anywhere. It's spread over 50 feet or so. On the other hand, if he asked you what its wavelength is, you could give him a reasonable answer. It looks to be about 6 feet, the wavelength being the distance between peaks, or repetition of the wave. By contrast, if you give the rope a sudden jerk, figure 1.9, right here, you'd get a relatively narrow bump traveling down the line. This time the first question, where precisely is the wave, is a sensible one, and the second, what is the wavelength, seems nutty. It isn't even vaguely periodic, so how could you assign a wavelength to it? Of course, you can draw intermediate cases in which the wave is fairly well localized and the wavelength is fairly well defined. But that there's an inescapable trade-off here. The more precise a wave's position, the less precise its wavelength, and vice versa. A theorem in Fourier analysis makes all this rigorous, but for the moment, I'm only concerned with the qualitative argument. Fourier analysis is super cool. We're not really going to look at it in this class, but interesting if you want to dig a little deeper. This applies, of course, to any wave phenomenon, and hence in particular to quantum mechanical wave functions. But the wavelength of psi is relative to the momentum of a particle, but is related to the momentum of the particle by the de Broglie wavelength, or the de Broglie formula. P is equal to h Planck's constant divided by lambda, the wavelength, or it's equal to 2 pi h bar, the reduced Planck constant, over lambda, the wavelength. Thus, a spread in wavelength corresponds to a spread in momentum, and our general observation now says that the more precisely determined a particle's position is, the less precisely its momentum. Quantitatively, the uncertainty in x, the position, times the uncertainty in p, the momentum, must be greater than or equal to h bar, the reduced Planck constant, divided by 2. This is Heisenberg's uncertainty relation. And it's not even related to quantum mechanics, it's just related to wave mechanics. Pretty cool. Where sigma x is the standard deviation in x, and sigma p is the standard deviation in p. This is Heisenberg's famous uncertainty principle. We'll prove it in chapter 3, but I wanted to mention it right away so you can test it out on the examples in chapter 2. Please understand what the uncertainty principle means. Like position measurements, momentum measurements yield precise answers. The spread here refers to the fact that measurements made in identically prepared systems do not yield identical results. You can, if you want, construct a state such that the position measurements will be very close together by making psi a localized spike. But you will pay a price. Momentum measurements on this state will be widely scattered. Or you can prepare a state with a definite momentum by making psi a long sinusoidal wave. But in that case, position measurements will be widely scattered. And of course, if you're in a really bad mood, you can create a state for which neither position nor momentum is well defined. Equation 1.4 is an inequality, and there's no limit on how big sigma x or sigma p can be. Just make psi some long wiggly line with lots of bumps and potholes and no periodic structure. And we are done the chapter. So guys, if you sat through this whole video, thank you very much. Drop a like, drop some comments, explain to me how you feel about this. I don't know if I'm going to do this for every chapter because it's so long just to read this. I think it's better for you guys to read it. I'm just showing you that you can read this thing. It's like confusing, but it's good to read through it. We're going to do some problems. Maybe for future videos, I'm going to read a little bit and then do some problems because I think the problems kind of give you a better sense of what's going on. If you just watch me read for an hour and a half, is it really that valuable? But let me know. Thank you guys as always for watching. Drop a like, follow, and yeah, send me some comments of things that you want to see, even not related to quantum mechanics. We could do some math or some stuff, but for this fall term, we're going to focus on quantum mechanics. Thank you guys for watching. Peace.